If you are new to the Azure Machine Learning Service and you want to discover how to transform your existing Python scripts to log values to a central space in the cloud and later on run the whole script on an external compute target, then this is the right video for you. Hi, I'm Sasha. Welcome to this channel. If this is your first time here and you want to learn more about machine learning, advanced analytics and cloud computing, start now by subscribing to this channel and don't forget to click the bell so you don't miss anything. A few weeks ago I published a 5-part series about how to use a DevOps pipeline of your choice to automate Azure Machine Learning Service. And a question which came up quite often was, how do I reuse my existing training scripts? What do I need to change? What can I add to those scripts to make most use out of that service? So let me demonstrate this step by step on a simple Keras script. So first of all, I'm importing the Keras libraries, in this case the ones out of the TensorFlow package. As you can see, this is currently TensorFlow 2.0. It's a GPU build and currently that machine has no GPUs built in. So this is false. Next thing, and I will explain why I'm doing that in a minute, I'm creating a folder. And up next, I'm downloading the sample files. In my case, I'm using the Fashion MNIST dataset, which is built into the Keras package. So let me execute that. And this is, of course, first downloading the images. These are 70,000 grayscale images of different things like dresses, t-shirts, boots and other things. And the first thing I have to do is, of course, normalize them. Since these are grayscale images, I can just divide them by 255 and I get the normalized version out of that. And I splitted that already into a training and a testing data set. So in this case, 60,000 images for training, 10,000 for testing. And I'm reshaping that to the proper shape for later processing. Up next, I want to show you one of those pictures. Again, here, for example, a picture of a t-shirt. And then for testing purposes, I'm creating a lookup dictionary for all those labels, and the labels are currently in the format that the first 4 images, the first one is a 9, which means it's an ankle boot. The next 2 images are zeros, which means these are t-shirts or tops, and the 4th image would be a dress. To be able to train that, I'm converting them into a categorical view, which means that each of those 4 images will be represented by an array with 10 values, where the one with the right label is set to 1, which means 100%. That's the goal I'm aiming for. So means that's the 9, and these 2 are the zeros, and that one is the 3. After that, I'm defining my model schema. I'm using a sequential, creating a convolutional neural network with 2 convolution layers, 2 max pool layers, 2 dropout layers. I'm flattening those things, and 2 dense layers. The first one's all with a ReLU activation function. The last one, of course, with a softmax to get the probability for each of those 10 outputs. So I'm creating that and visualizing those. So that looks good. After that, I'm defining my loss function, which is a categorical cross entropy, and I'm using an Adam optimizer for the training, and I want to get the accuracy out of that training. So let me add that, and I'm also defining 2 callbacks for Keras. So one for early stopping, which, by the way, in those 24 epochs, which I defined up here, normally doesn't happen. So just if I really want to overtrain those or train way more epochs, then the early stopping would probably kick in. And I'm defining a second callback to create a checkpoint file. And as you can see, and that's why I created that folder, I'm using that project folder to store the checkpoint file as well as the exported model later on. Then I'm doing the fitting, which takes round about 10 to 20 minutes to train those 24 epochs. I'm going to fast forward and show you in the meantime some further iterations of that training script. After this training is completed, I'm going to do an evaluation of the model with my testing data set and print those test accuracy and loss to the screen. And last but not least, I'm going to show the whole history of those 24 epochs, do some testing if everything works fine with the new model, and then exporting the model first as only saving the weights to an H5 file, then saving everything, the full model, into an HFH file, as well as the whole thing only in a JSON format. So I'm creating in the end 3 different types of exports of that model. So that would be a typical Keras script for an image classification model in the end. If I want to add the first tool out of the Azure Machine Learning toolbox, that would be using the logging. So if you go to the newly designed representation and go to experiments, so that would be the first tool I want to use. So going to the fashion MNIST, I ran that before. And as you can see, I had different failed and completed test runs to play around with the bits. Let's go to the 5, for example. And as you can see, I'm currently using that only for logging. For example, logging the training loss, logging the training accuracy, logging the validation accuracy while I'm running through those 24 epochs. Maybe adding an image or adding an image of a plot, or for example, specify the test loss and test accuracy after I did the evaluation, and so on. So I could use those, for example, as the first step. To be able to do that, switching back to the first iteration of my Fashion MNIST notebook. And again, this would mean that I'm just importing my stuff. I'm still on the same Jupyter server. And the first thing I have to do to really connect that to Azure is loading, of course, the Azure ML SDK, which is just a pip package I installed on that machine. And after that, connecting it to the workspace. So let's do those 2 steps. First, loading the SDK. I'm currently using version 1074, and then connect to my workspace. In this case, the name of the workspace, the region where that workspace is located, as well as the name of the resource group. And since I'm running already in the Azure environment, I didn't have to log in. If this would be a completely local notebook server, it would have asked me to log in first. So that's why this is not asking. I'm again creating a project folder for the output files, downloading the dataset, showing my t-shirt image, defining my labels, reforming my labels, defining the schema of my model, and compiling the loss and optimizer function. And the next thing I would add to that notebook is specifying the experiment. The first addition was more or less logging into Azure, and now I'm specifying that I want to log to the Fashion MNIST experiment. So I'm creating that, and if I just print that experiment to the screen, I get a pandas data frame, which is just delivering me the name of the experiment, the name of the workspace, and a direct deep link into the page you already saw, so the experiment. After that, I'm defining my callbacks, and down here, I'm really adding the logging functionality, which means now I'm tell the system experiment, please start logging here. I put that into a try catch block, because if I'm catching the exception, I can specify that the run has failed and print, for example, the error message. And the part from the previous notebook which is still there is, of course, the training itself. I could have used a kind of a callback mechanism to see live what's happening in the fit method. I decided to not do that and just do the logging afterwards, which is, from my perspective, okay. So I can, after the training has been completed, let me execute that. I can, for example, log a list of values, in my case, the training loss, the training accuracy, and the validation accuracy, as well as do already the evaluation in the same box, print and log the Scala values into my experiment, and last but not least, for example, use the matplotlib library to create a plot and again store that plot as an image into the system as well. And after that, I'm specifying the whole run has been completed. So this is still, because of the, this is doing an evaluation twice, so that's not needed really. And I can specify the plot, so that's still from the old script. And last but not least, I'm doing pretty much the same thing, testing my model, so creating a function to test that, doing the pure testing, and then exporting the 3 different types of model files in the end. So my model JSON, my 2 H5 files. And last but not least, I'm uploading the model files to the experiment, to the run of the experiment as well, so that this is available for other data scientists ready to use in the end. Or I can specify that later. It's kind of a documentation again, just using the run.upload file command. So these are just a few additions to be able to use the experiment service. So this is more or less the first step. Really just adding the experiment functionality into the script itself. The next logical step from my perspective would be that I'm not only training on my local Jupyter server, but I also want to push the whole training to the cloud and use, for example, functionalities in the cloud like the GPU hardware or other things. To be able to do that, I exported the whole script, so the log to Azure, the version 2 script, into a separate Python file. Importing everything. But in addition, I'm importing the machine learning SDK, but also the run object out of that azureml.core.run namespace. Then I'm just printing the whole relevant information, like which TensorFlow version, is it a GPU build, is the GPU available, what's the version of the ML SDK, and specify a folder for the outputs. And since this Python file will be run within an experiment already, within a run, I can just get the outer run as an object back. So just run, get context, so where am I running in the end, and get that run back. And after that, I'm downloading the files, reshaping them. In this case, I'm logging also an image to the experiment service, specifying the model structure, do a model summary, again, what loss function, what optimizer I want to use, my callbacks, doing the training itself, and again, logging everything to the existing run, logging the Scala values, logging my plot, and exporting my files to the output folder. There are some special folders like logs and outputs, and I used already on purpose the .outputs folders, which would automatically put all those files which are stored in there automatically to the right position in the experiment service. So that's why I don't have to upload the things. What I also could do in here, for example, use the model.register functionality of the SDK to directly lock the model to the version control for models. But I decided to not do that in my example. So after I created that separate Python file, I could completely create a new Jupyter notebook, which is in this case also making use of additional VMs or hardware or other things out of the cloud. Again, I'm importing my SDK. I'm connecting that notebook or get the object of the workspace back, and again define a project folder for the output, but also a training folder which I use to put my Python script in. The reason for putting that into a separate folder, I will explain that in a minute, but I'm just copying from my prepared training script or train folder my training script into a separate folder out of that project. So let me execute that cell as well. And then, like I did in the previous notebook, define my experiment. In this case, I also want to define the target where I want that script to be run on. In my case, I'm using an HPC system called Azure Machine Learning Compute, which contains several machines of the same system. In my case, I'm using a standard NC6 machines, which means that these are GPU enabled. The N series in Azure is GPU enabled. C means that I'm using a Tesla K80, and 6 is the number of CPUs. And for every 6 CPUs, I get 1 GPU, which means that I've got 6 cores in here and 1 GPU. I'm using a dedicated set of machines, which means that I own those machines. They are completely ready for me to be used, but I'm paying also the full price. The other option would be low priority, which means that I'm using machines which might be pulled away when they are needed by somebody else, but I'm only paying while these are running for me. I'm only paying around about 20% of the original price. So it's a trade-off in the end. I can specify, since this is a cluster of machines and I can allocate several machines at a time if I need those, I can specify the minimum nodes of that cluster and the maximum nodes. Minimum 0 means that there are no virtual machines in the beginning. As soon as I start adding tasks to that AML compute system, it will start booting up, initializing and creating machines for me, and a kind of a cost threshold would be max node setting, which means that I'm not allocating more than 4 machines at the same time. And after the machines have been used, they will be automatically deleted, and therefore I'm specifying a 5-minute grace period, that I'm allowing the machines to be 5 minutes idle in the end before they will be really deleted and the system scales down. So executing that would tell me that the GPU cluster already exists. That was the name of the cluster, GPU minus cluster. But even if it doesn't exist, it takes around about, 30 seconds to be created, because there are no machines in the minimum nodes. So that means it's just an entry that I allocated a set of machines, or want to have them at a specific point in time. After that, I can specify the tasks I'm running on. Normal tasks would be just a Python script task or an R task. For example, I decided to use a specialized one, which is specialized for TensorFlow. There are several ones like PyTorch, CNTK, TensorFlow, and others. And in this case, I'm using the TensorFlow one. I'm using a source directory, and this is the directory where I put my Python script in. The idea behind that is that the whole folder will be uploaded to the cloud. In my case, only the Python file, but could also be some other related files, which I'm automatically uploading. So that's why I specify that source directory, that all those files will be available for my AML compute. I'm specifying a compute target. That again could be several things, like a data science virtual machine, like a Spark cluster, Databricks, a Hadoop. In my case, I'm using the AML compute. I'm specifying the entry script, which is my Python script. And I could also specify arguments for that script, which I didn't do because this script has no arguments. I'm specifying the number of the machines I'm going to use. That would be only 1. I also, of course, have to specify what are further dependencies which I need. Since I'm using already the TensorFlow task, TensorFlow will be already installed. That's why I specify the version of TensorFlow 2.0. But for example, I also need matplotlib, and that's why I specify a conda or optionally pip packages, which will be automatically installed. I also want to use the GPU versions of those packages if possible. So I'm going to create that task as well. So after that task has been created, I can submit that to the cloud and wait for the run to be completed. And as you can see in here, if I'm executing just the run, pretty much like the experiment, I get a direct link to that run. And down here, since I said show the output, I see the whole process of that system. And as you can see, this is creating a Docker image for me. And since I did that previously, this is reusing an existing Docker image for training. So it's downloading that. And when this has been completed, it will turn on the machine and start training. Since this is completely in the cloud, I can also decide I don't have to go to the portal. I can tell the run, please give me the metrics afterwards, store that in a separate object, and I can use that dictionary to, for example, directly access the loss and the accuracy which I stored while the training was running, as well as, for example, create my own charts out of the training accuracy which I uploaded and the validation accuracy which I uploaded to the experiment service. And last but not least, I can get all the files which have been generated and uploaded and download the files to my local project folder. Let me check what's happening. Checking number 12, which should be the one in the cloud. You can see I logged, for example, the t-shirt. I have already the accuracy and the charts. So that's the one which ran on my GPU cluster, as you can see in here. That should be nearly done. Let me check that. Perfect. So as you can see in here, this is already the run on my GPU cluster. So it's specifying that it's a TensorFlow script, that there is a physical GPU available. So that's my NVIDIA Tesla K80. It says it's GPU enabled true. That's the ML SDK which I'm using, and this is more or less the whole training process. So downloading the files, specifying the schema, starting the training, running the training. Here we go. So it's exporting the models to the output folder, finishing up everything, and it says that the job has been completed. And as you can see, that's my loss function which I logged, my accuracy of the evaluation which I logged, another plot which I generated out of those two metrics. And as you can see, several files, and I'm downloading only the ones from the output folder, so my checkpoint and my 3 exported Keras models. When I go back to the experiment service and switch to the output tab, so here's my checkpoint file, my 3 exported models, as well as, for example, my plot or my t-shirt which I stored, so just an image which I uploaded. So I get all those informations back, as well as the logs which I generated while the training was happening. So I can see everything that happened under the hood, as well as the training itself. So in the end, I went from a typical Keras script, adding just the logging mechanisms of the experiment, up to running everything outside of the system.